Welcome to my Commodore 64 Games Memories. This is where I look at old games and some of the technical details behind them. Let's get into it. Today we have Exile, but part 2 this time. What I want to do in this video is that I want to show you some of the steps that I go through when I'm trying to reverse engineer parts of games, if I'm so inclined. To do this, first of all, what I need to do is that I need to find a good entry point for the game, usually the main entry point after the game has finished loading. To do this, what we can do is that we can start the loading process and then create some kind of break point which will hopefully stop in the main part of memory, because as we can see here, the loader is executing right up at the top of memory, and the breakpoint that was set actually was in the main part of memory, and we kind of guess that this is the main entry point for the game. It's at 560E. If we have a look at the CPU history, we can see that it's actually done a few instructions, 4 actually, way down at the beginning of memory, practically in the extended 0 page, just in the screen memory actually, and then it's returned from an interrupt routine. So let's disassemble the code at 700 onwards. We can see that it was doing some kind of DD00, so serial port. Usually that's the disk serial port, because this is the disk version. It looks like it's doing a final check with a memory location 6AA in hex containing FF. If it does, then it seems to jump over the what looks like some kind of like reset or something like that. It's using, well, actually it's going to 712 in hex, which is jumping straight to 72D, and then 72D does a jump to 560E, I think, something like that, based on that history. It looks like 6AA was probably some information just read from the disk, probably as a final protection check or an EOR check or something like that. So this does look like it's just jumping straight into the game code. I mean, it looks like the fast loader routine does have the option of understanding how to relink a basic program and then run the basic program, because you can see it's restoring the 0 page registers for 2E and 2D and JSR into A659 and A533. These are all in the basic part of the ROM, usually containing most of basic routines. But it's skipping this code, it's skipping what looks like the basic initialization code. And that's because this program doesn't start basic code. It just starts with the jump, so that's why it seems to have skipped over all of that. I'm guessing that this fast loader and or the protection scheme was some off-the-shelf product. Just adding some notes here for future reference. So I'm saving all of the memory here and putting a little note that the start address that I think it is 560E. All of the memory, meaning 200 all the way up to FFFF, which is at the end of memory. Not saving the stack, not saving the 0 page locations, because I'm pretty sure that the code at 560E is going to do a comprehensive initialization. So what I can do to check this is that I can use my compression tool, which compresses virtually the whole of memory, because I've saved out the whole of memory as a file, and I can then check the output length, and it's relatively short. And then I can run the compressed output file in a separate emulator using a newer version of Vice, and we can see that the game runs. So I think that we've got a good copy of the main memory here that we can actually do some work with later on. Now I have noticed that there are the remnants of the bitmap loading screen in memory, which is fair enough because it's actually still shown in the Vice view there. So what we can do is that we can try and clear out this memory used by the bitmap. We know what the memory addresses are. We can double check those by using IOD000, which shows the IO state, the internal state of the emulated VIC chip, the video chip. and it's telling us that the video memory is at 5C00, which is there, and it's showing bitmap memory, which is at 6000 in hex. So we're just going to clear out all of this. I have a feeling that the screen at 5400 is the color memory, so I think that gets copied up into color memory at D800, but that's separate color memory. We're not saving that out when we do a complete memory save. We're saving RAM, not the color memory, which is on top of the RAM. There is RAM underneath the color memory. So anyway, we'll just clear the whole lot of memory there, 5800 all the way up to 7FFF, and we should see those screens and the bitmap data go blank. The at symbol is the 0 character in the character set, therefore it's nice and blank memory now. I'm just going to save that as an extra file, call it memclear1, making a bit of a typo there, there we go. And then to double check that, what we can do is that we can use the compression tool again to compress that cleared file. Now this is useful, these kind of steps are useful if you want to find out how to make say for example a single file of the game and compress it into a single file if you don't really care about seeing the loading screen, for example, or if you don't want to run the disk version all the time and do, wait for the loading. You can do this and you can clear the memory and you can compress things better if you know for sure that the memory is not being used. We can see that the output length is drastically reduced because it doesn't have to compress all of the bitmap data, which is great. Fantastic. Anyway, so we have two good files now, I think. We'll just run that compressed output now just to make sure. Bling, 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 bling. And yeah, game seems to start okay. I'm kind of assuming here that the game protection checks are not going to kick in. I hope that they don't. This game is quite famous, or infamous if you like, for having difficult protection checks, but I'm not trying to make a completely working game. I'm just interested in the game working at the beginning and the protection checks hopefully not happening later on. If anyone knows what the protection checks look like when they do detect that there's an issue and make the game unplayable or uncompletable, then please do add into the comments section below like a link or a description explanation about what those protection checks look like when they work, and I'll see. Now this is interesting. I noticed in the screen data, in this code here, which looks like temporary initialization code, there are some things like FX1380, FX4 Now, this is not Commodore 64 Basic. If anyone knows what this is, then it's BBC Basic. That's why I looked at this website here. The only reason why I know it's BBC Basic is because I used to do BBC programming. BBC Microcomputer. It was a very popular computer in the UK, and it was in the schools everywhere practically, and so I'm very familiar with this basic. So that's what made me think of this. And look, there's insert character into keyboard buffer, and then there was also FX42 as well, which also does some stuff. So I'm intrigued about why BBC Basic fragment of a BBC Basic program is in memory there. But I don't think it has any impact on the execution of the rest of the code. This code here at 5000 to 5800 and the data is temporary because I know that this space gets overwritten anyway by sprite data or character data because it's in that Vic bank which is being used for character data, screen data and sprite data. So this is the temporary initialization code. So I'm going to put ranged breakpoints that don't. I'm going to put ranged breakpoints that basically exclude this range of memory, so that after the temporary initialization has been done, it will then run the rest of the basic code. And then once I know that it's starting to run, not the basic code, the game code, once I know that it's starting to run the game code outside of this initialization routine, then I'm going to look for or break on any kind of like writes to the sprite cache area, because what I want to do is that I want to find out how the sprite cache works now, and I want to see if I can get that routine working independently so that I can see all of the animation frames that are in the game. Because the sprite caching and the sprite decompression was actually quite interesting, because it seemed to have a good way of having lots of animation frames in memory, but you know, copying them in and stuff like that on demand. So I want to have a look at this in more detail. So we know that it's not going to be doing any code in the VIC bank that's being used to display graphics. So we'll put the breakpoint after that, up until the end of memory. And I think just to be on the safe side, I'm thinking we'll put a small ranged watch point as well for reading or writing memory locations there, just to see if it picks out anything to do with the disk. Okay, well, it seems to be overwriting the memory that was previously used to store the result of the protection check, so I don't think that we need that ranged watch point there, so I think we can probably delete it. It seems to be moving data from somewhere further up in memory over that lower screen memory, the default screen memories, right? So we'll get rid of that ranged breakpoint, and we'll just let the temporary initialization routine start working. Okay, here we go. So watch the memory view as well in ICU64. This temporary initialization code looks like it's going to be doing some memory shuffling and some initialization of the game data. Not unusual, because it's got some blank memory there, and I know that memory is not blank. So we're going to see what happens. There we go. Quite a bit of memory shuffling going on. So now we've started the main game code, let's put a breakpoint on the sprite memory so that we can see when the sprite caching routine starts. Oh, look, what is this? We have the background visible now, and we seem to have a hit for the first sprite frame coming on. So, and that Y register is suspicious to me, because it's set to the size of a sprite. So the sprite data is 3 bytes times 21 rows. So it's clearing what looks like a sprite. This looks like, there's probably more than one sprite decompression piece of code, but we'll see. But this looks like one piece of code which does sprite clearing, and it'll clear a sprite somewhere there in the debug view, I'm guessing. 4FC0 is the last sprite in the sprite cache. So it's the first. If the sprite cache goes from back to front, then it's going to be the first sprite which is allocated. Okay. This game, it displays the background first, and then for a couple of frames, and then the sprites seem to come in a little while later on, after those first couple of frames. It's interesting that it clears the whole sprite first and then does some copying. That tells me that the source data that it's copying is at least partially compressed, or it's only storing the absolute minimum and maximum ranges that it needs to in terms of sprite data, so that if the sprite had blank pixels up at the top or at the bottom, then it skips storing those in the source memory, for example. So let's watch that. There we go. Looks like it's cleared it. There was only a couple of pixels there being cleared, I think. And then we have a whole bunch of stuff. So this is intriguing. It looks like it's reading in at least 3 bytes, and then doing that first AND with FF is superfluous. The second AND is okay, and then the third AND with 0, you could have just skipped the data, but okay. Seems to be doing quite a lot of arithmetic. I think it's updating half a sprite. Now, if the sprite data was compressed or packed into memory to such an extent that a narrow sprite takes less memory, which is a good optimization to do, then this routine would kind of make sense. Okay. Also, if the sprite data was being read and then it was being flipped by the table at 1500, then that would also make sense. Okay, so bear that in mind too. We can see that the first frame for the sprite it's either the player character facing left, or it's probably that enemy which steals the destinator coming in and flying off to the left, right? So I'm hoping that, yeah, 7.7 and 7.8 are low and high 0-page indirected pairs being used consistently throughout the whole code. It would make it easier to put a breakpoint on the... Oh no, the breakpoints don't... No, I'm using the old version of Vice, because it's ICU. Don't think that... Yeah, breakpoints in 0-page memory don't work. Watch points on 0-page memory don't work. Slightly annoying, but that's okay. Never mind. We can restore the watch point for the store to sprite data now. Then we can see here that it's doing load and store, load and store, load and store. This looks like it is applying probably the teleport effect, because the enemy that comes flying in at the start teleports out, and it does that by removing pixels from the sprite data, which is what this does. But that's what I'm guessing. That's what that code does. When you're debugging this and trying to figure out what code does, you have to make some educated guesses, and you have to take into account the context of what is going on in the game at the time, and then apply the context of what you see in the game to what you think the code is doing based on the code structure. So that's what I think that's doing. And yeah, you can see once that code has finished executing, it has significantly faded out or removed pseudo-random pixels from the animation frame. Now there is another sprite update here, and this is the next sprite along at 4F80, which is going to be the one to the left of the one that's just been calculated, because the one that's just been calculated is at 4FC0, right? So a 4F80 is 40 in hex bytes previous, and that means it's the next sprite previous in memory. So it's the sprite to the left in the debug view. So let's put some breakpoints again, execution breakpoints, and yeah, you look at the ands, and instead of anding it at F4AA onwards, instead of anding it with F0 and 00, it's doing ands with 00, FF and 0F. So the sprite, if the sprite data is partial sprite data, then it looks like it's only doing the other half of the sprite, which is itself interesting. So I'm looking to see now where 7.7 and 7.8 are being calculated, because I have a feeling that wherever 7.7 and 7.8 0-page memory locations are being initialized is where it is at least figuring out the address for which sprite cache memory address to use, right? Which sprite cache slot, in other words. So it looks like that this is the beginning of the routine at F40A, right? Because we can see before it there is a jump, and it's not the jump anywhere within the code which updates the sprite. And this is hopefully common code which calculates 7.7 and 7.8. Hopefully there's no other code anywhere else. So we'll put a breakpoint here, because we think that this is the start of the sprite cached frame calculation update. Okay, so we'll store that little piece of information in our file for later on. This is an assumption at this point, but we can test that hypothesis. I'm definitely sure that that's not going to work. We'll just re-initialize the ranged watch point after the routine has finished. So that's the destinator. which is the thing that gets stolen, which is what we need to have to be able to fly the ship or whatever it is, right? This looks like a sprite clear. That's the start of the sprite routine. Forgot to put a breakpoint there, or rather it was probably cleared. So let's delete the ranged breakpoint. Right, and there we go. There's the switch sprite being created, which is the switch which locks or unlocks the door. And then, yeah, we've got a very obvious JSR to F40A there. We can see after the code there executes, it creates one more sprite each time. It's not skipping out any of the sprites or anything like that. So I think we can say at this point that we have a good entry point for the sprite cache update decompression routine, if you like. I think we can safely say that it's using some form of decompression because the source data does not look like sprite data. It looks like there is some compression going on there, whether or not it's only storing partial rows or rows in weird order, but there seems to be some expansion of the source data to the target sprite data, so we can say it's decompression of some description. Whether or not it's RLE, it's not RLE, but it's doing some extraneous data removal there. The source sprite data is packed in some way, therefore it is being depacked or decompressed. So anyway, we can see that there have been a few more frames now created, probably of the enemy teleporting in and then bouncing around, jumping around, and then they're going to teleport back out again. There we go. Yes, that's the game sequence. They've stolen the destinator. I think they look like the player sprite, but they're just coloured differently. It's using a different colour, that's all. So now I'm trying to understand the behavior of this code. F537 is storing or self-modifying into the code, so I think that there are some self-modified table updates here, probably low and high addresses or index values into the compressed source data, probably to identify each sprite frame. The organization of the source data seems to be swizzled 90 degrees or rotated 90 degrees compared to how Commodore 64 sprite data is usually laid out, and that's because it wants to use the index registers in an optimal way. These are sprite masks, actually. Look, it's going and storing it into the self-modified and immediate values here, so it's something to do with masking out unwanted data based on the source width of the sprite, which is cool. This one looks like a horizontal flip table, so it reads the source data, then does a horizontal flip with a mask and then stores. Also kind of cool. Also rather expensive to do. It's doing a double lookup basically, and a bit of extra maths. To be honest, it doesn't need to do that extra maths. It could have some sprite routines optimized for each width. That would be better. Wouldn't take up that much extra memory either, to be honest. And it would certainly be quicker. Although the sprite cache, of course, definitely helps to iron out the execution time of, well, helps to smooth out the execution time by doing all of this flipping and masking and teleport out effects and teleport in effects and stuff like that. So I'm just trying to understand the behavior of this code a little bit more. The more I look at it, then yes, the more this code does seem to be oriented differently to the normal memory layout for Commodore 64 sprite data. See, it's loading in this case from 25E1, 26E1, 27E1, but these memory addresses are self-modified. We can see here that the data looks a little bit like graphics data, but we can see that it definitely doesn't look like sprites. We've got some characters and things like that, yeah, cool, but we can see that it's definitely not sprite data which the Commodore 64 knows how to display it all by itself. So let's put a breakpoint at the beginning of the routine again. That's the Sprite cache update routine. What is that common entry point? Or what we think is the common entry point? Well, it definitely looks like it, right? And let's study this a little bit more in some more detail. So the X register is at 2F, which seems to be an index value into the Sprite cache slot, the Sprite frame slot, in other words. It takes X, it's doing some adds, shifts, rotates, adds, and some stores into 77 and 78, and that calculates the address. So it's doing some maths there. I'm pretty sure that this is the Sprite cache slot for the X register. Now I'm not moving, there aren't any other sprites moving. Warp mode is turned on still. Flipping my direction still doesn't create any new sprites because the sprite frame is already there in memory. This X register now, because I've decided to move, it is creating a new cached sprite because it wants to decompress a new frame. So we can see there it created a couple of extra frames in the sprite cache. I really need to find out where it is setting the intended frame for the sprite now. I know the cache slot index, which is the X register, pretty short. I think it might be the Y register, but then looking at this code, it gets the Y register from 3C, which is a 0-page location, which is almost like a register, but not quite. I think it is the sprite frame. Now if I override whatever value is in 3C and I let it create a new cache sprite by decompressing what I hope is always going to be frame 0 now, then the frame that gets decompressed should be the same as the adjacent one, and it is. Look, we've got two of those horizontal flying to the left. So it decompressed the same frame twice when I overrode the frame index. So that's cool. I think we're getting somewhere with understanding how this routine. We can test this by writing some extra code, and I definitely do think that we should test this hypothesis, this extra data, information that we have here. So I'm looking now for some blank memory, for some spare memory that I know isn't really going to affect the game, and of course the really blank memory, the spare memory that we have, is going to be at 4.8. It's going to be these character set data, right? I don't really care about the character set data. I know that it's not source data for anything. I know that it's not going to be code for doing the decompression routine for the sprite. So let's put the code there. Now what we can do is that we can initialize X with the sprite cache slot, which is 2F. We can increment 3C, which is the 0-page address for what we think is the sprite frame. We can do a JSR to the sprite update, and then we can just do a jump to 4800, and then we can go 4800. And what this should do is that it should continuously decompress new sprite frames into the last slot. It'll rapidly decompress new sprite frames always in the last slot, hopefully. What we should really do is that we should just do a test for the raster position. We'll just slow it down a bit so it's not stupidly fast, I think. D012 is the Vic raster, which is the vertical position of the raster beam as it's moving down the screen. So if it's anywhere on the screen apart from line 0, basically, then we will just do a delay. Now we can run that code. You see it's initialize X, increment the sprite frame, decompress the sprite frame, and then run the code. There we go. We'll get rid of the breakpoint at the beginning of the sprite, and there we go. We can see it is rapidly decompressing lots of sprite frames. Some of them are garbage, and that's probably because not all sprite frames are initialized with data. I'm rather assuming here that the whole game doesn't have all sprite, or all 256 index values of sprite frames. I'm pretty sure that there are some not being used. Let's change the sprite cache index block. And there we go. We can actually see from the memory view, look, it's reading in a whole bunch of data in nice rectangular blocks for each sprite frame that we're decompressing. So I think we can say here that it is a, like a table-driven, partially compressed, packed sprite data format with this decompression routine. So that's cool, right? So we've understood how that routine works. I'm just frame stepping through this so that we can see individual sprite frames a little bit better, just to really validate that, and it does. So we'll note down that code as code that works. Looking at this code, it also accesses some other 0-page memory locations, so 3.5. I think that might have changed the direction, maybe, of the sprite that it was facing. So it's doing a plus or minus check, right, with the contents of 3.5. It's also doing an EOR with 3.8. 3.8 currently contains 0. Let's see if we can get a nice looking sprite on the screen first. Let's try and work with a valid sprite, because as we can see, some of the decompressed sprites are not valid frames. So the laser cannon facing right is a good one, right? What we can do is that now we've got a laser cannon there, we can no-op out the increment for the sprite frame, and we know now that we are always decompressing that same sprite, which is the right facing laser cannon. Now if I put 3.5, make it contain 1. Well, if I make it a negative number, which is like 8.0, set the negative bit, the sign bit basically, it makes the sprite half height. Well, that's interesting. Maybe not entirely useful, but okay. I haven't played that much of the game recently, to be honest. I don't remember if half height sprite mode is useful anyway. Anyway, the other location was 3.8. Doesn't seem to do much. Let's set it to FF, see what that does. Oh look, it's upside down and facing to the left now. This is nice. That's rather special, isn't it? So this is how the game is... this is how the game is storing so many sprite frames, is that it can flip sprites horizontally and also flip them vertically as well. That's clever. Hence that what I thought was a mirror table in the sprite data probably is a mirror table, right? Mirroring, horizontally flipping or mirroring the sprite pixels that are being used in the sprite data. Nice. Let's put 8.0 in there, see what we get. Horizontal flip. The sprite for the big laser cannon is now facing to the left and standing upright correctly. Let's make it 0F. It's facing to the right again. F0, upside down and to the left again. So it's just seems to be the upper nibble which is controlling the flips. Okay. Not the lower nibble, doesn't seem to have any visible effect on the sprite, I don't think. Let's put C0. Well, there we go, the last two bits, 8.0 and 4.0 all together. Let's change that to be now, and then it's facing back to the right again. Good. So yes, 3.8 has X and Y flips in those last two bits. So to really test this code and this new information, what we can do is that we can write some better code. Now this is a new assembly file that I've been working on. It puts some code again at 4800. It defines all of the things that we know hopefully about this particular part of the sprite cache decompression code in Exile. It sets the interrupt flag and clears the screen memory first of all. It increments the border. It resets the joystick port, CIA port, data direction register, and it also sets up the memory so that it has a nice black screen. We don't really want the background there. And then it sets up the background, and then it basically does that call to decompress the sprite into a known sprite slot. And then what we do is that we set up the sprite hardware registers to display a 2x1 sprite and a 1x2 sprite, so 2 sprites together horizontally and vertically, and then a grid of 2x2 sprites with different sprite index values corresponding to the up to 2 to 4 sprite caches. Okay, so that if we decompress a large sprite, then if it's a 2x2 grid, then it will hopefully display the larger sprite as a 2x2 grid. These flips are under joystick control, the frames are under joystick control, left and right, and up and down control the horizontal and vertical flip toggles. Okay, if fire is pressed, then it will jam with the jam instruction, otherwise it will loop around. Okay, so we need a way of putting this code into actually get into the game when it's running. So what I'm doing now is that I'm using my remote debugger testing language to automate the Vice remote debugger in the emulator. So it assembles the source code, starts Vice, connects to the remote monitor port on the network, issues these commands, which basically loads the single file version that we saved out earlier on, right at the beginning of this video. It waits for the first breakpoint at F40A, which is the sprite decompression code. Then it injects our new code, and then it runs that new code, allowing us to control it. So this is why we get into the game, and then we get rid of the background, and then we're able to control which sprite frame that we see. And I can scroll left and right through the sprite frames until we get to a good looking sprite frame. Here's a crab, for example. There's the destinator, the flask, Fluffy, imps, the cannon, and the bush, switch there that we saw flying around. Scrolling through all of these sprite frames in a controlled manner under joystick control. We can see with the raster, with the color bar change time, we can see how long it takes to decompress some of the sprite frames. We can see how there's a robot, there's one of the enemies, there's more of the imps, there's a player. Now if I use the flips, there we go, flipping left and right. Under joystick control, we can see how long it takes to decompress that sprite frame. And it takes slightly longer to decompress a flipped frame, and we can also do the inverted, the vertically flipped sprites as well. So there we go. We can see that the vertical flip doesn't take any extra time, but the horizontal flip does, and that's because it is indexing into that mirror table. So that's cool. I think I'll leave that video here. If you like these kind of technical deep dive sessions into old Commodore 64 retro games, then please do consider liking or subscribing to this channel, and I hope to catch you around next time. Thank you very much for subscribing, and have a great day wherever you are.